Okay, so this is lecture 10, 23rd of April 21. So before I begin, let me just summarize two things, uh, since we are going to get into a very interesting topic today. So far, what we have done, we have discussed the free vibration, okay, of undamped and damped.
Professor, could you focus your screen a little bit more?
Oh, sorry about that. Yes, I'm sorry. Here we go. Sometimes it does it. So thanks for bringing that to my attention. So far we have discussed the free vibration of undamped and damped uh, systems, single degree of freedom systems. So I just want to remind you something that, or rewrite something that we will use later, and even including the lecture today, that the response in the case of undamped, okay, an undamped system, the motion was of this form, right? A cosine omega nt plus B sine omega nt, which of course you could write that also in this alternative form, right? Sine of omega n t plus theta. If you use the initial conditions that are, say, u at time equal to 0 and u dot as equal to 0, let's say this is at u at time equal to 0, this is u dot at time equal to 0, or at some point, that equation for the response will look like this in terms of those initial conditions, okay? So this was for the undamped system. So this is the general form of the equation of response in terms of initial conditions. And now, in the case of damped systems, I want to emphasize that, as I said before, last time, when we're talking about the free vibration of damped systems, okay, we realize that we are dealing with three possibilities. Damping ratio, which we define what it is greater than 1, which we call that overdamped system, right? In that case, the response was an exponentially decaying function. Or damping was ratio is equal to 1, which we call that critically damped system. And in that case, the response will reach equilibrium, but continues a decay, an exponentially decaying function, because the envelope to that uh, exponentially decaying function, as we saw, was a linear function of first order. But as I said, these two cases are not that significant, and in mechanical vibrations or even in structural dynamics, we rarely come across cases that they're overdamped or critically damped. So the focus of what we do from now on throughout the rest of the course will be on underdamped systems. As I said, almost 90-some% of all systems in that we encounter are underdamped. So in this case, the response was of this form, right? A to the e to the power of zeta omega n t sine omega n t plus theta. That were these two were the unknowns, right? First of all, it's interesting if you compare this form with this. This is the general case. In other words, if you put zeta, which is the damping ratio, is equal to 1, this reduces to 1. And I'm sorry, this is omega dt, not omega nt. Omega d, which is 1 minus zeta squared omega n, since zeta is equal to 1, 0, this would become 1. So omega d becomes omega n. So this reduces to that form. Okay, so this is a general form of the response of the system uh, when it's vibrating freely. In terms of the initial conditions, let's say at time equal to 0, you have the value of the displacement, and you have also the value of the velocity, which is u dot naught. Okay, if you substitute those into this equation, meaning that, well, you put time equal to 0, so this becomes 1, left hand side becomes this, right hand side, this is 0, would be just sine theta, take the derivative, so you can, use this initial condition. You have two equations, two unknowns. I don't go through the algebra of it, but the response will come out to be of this form, okay? The shape of the response will be this, zeta omega n. After you do all the simplifications and all that, you get this equation, cosine omega d t times u dot, initial condition, plus u dot naught over omega d times sine of omega d t. So this is the response given the initial conditions. Again, if you substitute for zeta equal to 0, this becomes 1. This term cancels out. This becomes omega n. This becomes omega n. You see that you will get to this equation. So the response of of a damped system is really the general, of course, for the free vibration, is really the general form that you can also get the special case, which is undamped system. But let's move on and let's see what we are going to further study about these damped system. So as I said,
Can you show the bottom of the last page for 1 second?
absolutely, sure. Oops, not that one here. This one, right?
Yeah.
Sure. So let's make some now. I will focus on this, the case of underdamped, and the first thing I will do, let me just do one problem, and then we're going to discuss this further. Okay, but remember though, as I emphasize again, this is the case that we're going to be dealing with throughout the course, and this motion is a sinusoidal motion with a decaying amplitude. That's what this is. okay? And this is due to the reason that this is the equation, right? A sinusoidal motion with a decaying amplitude, okay? Now, oh, where this is the amplitude, e to a times e to the minus zeta omega n t, and this is that this is the uh, motion. This is the the period of the motion. Okay, the frequency is 1 minus zeta squared times omega n, and the form of this response is a e to the minus zeta omega n t times sine omega d t plus theta. Okay, and you saw how it is in terms of initial conditions. So with that said, first, let me do a problem, and then we will discuss this further. This is an important case. We are going to spend some time on that. So I'm going to do an example problem. Let's say you have a rigid beam connected to a damper at this point. Okay, I did it longer than I should have. Let's say this distance is 3/4 of L. You do have a mass M at distance L from here, and this is the tip point of the beam. Let me get rid of the rest because um, the whole beam is of length 2L. You do have a spring attached here with the given stiffness. The spring is located at one point L from this end point O. So this is rigid and massless. So we are going to look at this problem, find the natural frequency, evaluate damping ratio. As I said last time, the study of the free vibration of damped system introduced to us the second important dynamic characteristic of a system, which is the damping ratio. And we want to see how you can actually evaluate this, or do you find this? So I will first do an analytical, basically, problem, and then I will discuss how you find this ratio experimentally, okay? Which you do that actually in the lab. So we want to solve this problem, find omega d, k, m, and c, and set up the equation of motion. How do we set up the equation of motion? I will use free body diagram of the system. Let's say this beam is rotating this way. This is theta. So you have these two unknown reaction forces. You have a force due to the damper, F sub C. You do have a force due to the spring K. And then you have, of course, this mass here. So you do have also the lumbar force, which is the inertial force. And this is a distance L. So the moment of inertia is ml squared times theta double dot. Okay. So that's a free body diagram. So I will take summation of moments about O is equal to 0 this way. So I will get ml squared theta double dot plus f of c times this distance, which is 3/4 of L, plus f of k times this moment arm, 1.5 L is equal to 0. Okay. But what is f of c? F of c is c times the velocity at this point, which is the time derivative of the displacement. What is the time, this displacement, which let's say if this is delta c, would be 3/4 L times theta, right? If the angle is a small. How about the displacement here? Delta K would be what? Would be uh, 1.5 L times theta. So I would substitute for f of k. This is c times delta c dot. This would be k times delta at k, which,
Lester, we can't see what you wrote down there.
oh, sorry, I always do that. Shame on me. Okay, so this is a displacement at this point for the spring. This is the displacement for the damper. Forcing the damper is c times the velocity at that point, which is a derivative of this displacement. Forcing the spring is k times that displacement. So if you substitute for these in that equation, f of c, okay, first of all, would become 3/4 L theta dot, which is the derivative, times c. F of k would be what? Would be 1.5 L theta times k. So I'm going to substitute these into that equation. And if I do that, this is what I will get. Okay. I will end up with m L squared theta double dot plus 9c over 16 L squared theta dot plus 9/4 L squared K theta is equal to 0. You can see it here because this is 3/4 of L, right? Times 3/4 L, so 9/16 L squared theta double dot. So that's how I ended up with this equation. You can see that I have L squared these canceled out. So this simplifies to m double dot plus 9c over 16 theta dot plus 9/4 k theta is equal to 0. So this is the equation of motion in terms of theta. So in this equation, this is the m, or the m equivalent. This is the c equivalent. This is the k equivalent. So obviously natural frequency, which is k over m, right? Or k equivalent over m equivalent would be what? Would be 9/4 of k over m, or 3/2 of k over m. So that is the natural frequency, one of the quantities that we were asked to find. But what is the frequency of this system, undamped system, which is omega d, is 1 minus zeta squared times omega n. But what is zeta? How do you find zeta? Let's find zeta. Zeta is c over the critical damping coefficient, right? So it's the c in the system, which is 9c over 16. What was critical damping? That was 2m omega n. Okay, so it is 9/32 m omega n. But I like to, simplify this a little bit more. So, of course, 9c. Okay. So what I will do, I will substitute for omega n, which is K over M, right? And I write M as the square root of M times the square root of M. So this and this cancel out. So zeta is simplified to 3 would be 9 over 32. So it's 3 over, actually 9 over, I'm sorry, 9 over 32 of, okay, C. And this is 2 omega n. So, right. So would become, this become 9 over, uh, okay. After let me remind you, this was 2 omega n. So would become 9 over 64, okay, of C divided by K M. So that's going to be zeta, right? Let's see.
I think you had it right with.
I think so too. I think I made a mistake here somewhere because I have 9 over 16, right? C over 2m omega n. So I had 9 over 32, but right? Is that right? Is that what you're saying?
Yes.
I think it would stay 9 over 32 the whole time.
Yeah, that's right. 9 over 32. Yes, that's correct. Yes. All right. So that's the damping ratio. Okay. So damping ratio is 9 over 32 of C over K M. So this is another quantity that the problem wanted us to find. For some reason, when I did this, I have in my notes at 3 over 16. So, oh, I know what happened. You didn't catch me. You see, that's not the only mistake I made. Omega n was not this. Omega n was 3/2 of K over M, right? You see that? So if you do that, you have 9/16 over, okay, over 2 times 3 over 2. So this and this cancel out. 3 and this become 3. So this becomes actually 3/16 of C over K over. Yeah. You follow me? Okay. It's Friday, so I think it's okay to make these mistakes, right? Toward the end of the week, and okay, that's a good excuse. All right. Anyway, but let's now then find omega d, which we just left it as that before, as 1 minus zeta squared omega n. Now that I have zeta, I can write zeta squared would be what? Would be square of this, which would be 9 over 256 c squared over km. So I substitute that in here. I get omega d would be 1 minus 9 c squared over 256 km. Okay, this is this times omega n, which is 3/2 of km. This and this cancel out, right? And then this and this would be m squared comes out of the radical. So this would be simplified. And I take the common denominator here, and this would be simplified as 1 over 2m times 3/16 times 256 km minus 9 c squared. Because this, you took the common denominator, this comes out. So anyway, omega d would be further simplified as 3 over 32 of 256 km minus 9 c squared. So this is omega d, this is zeta, and that's omega n. The three quantities that the problem had asked us to find: omega n, zeta, and this is the frequency of the vibration of this system. Any questions?
What does that zeta say? 3 over 16?
This one?
No, the one above that you circled.
This one, 3 over 6, yeah, 3 over 16 times CO. See, I made a correction here because I had just said omega is k over m, but omega is 3/2 of k over m. So it ended up with after simplification to be this value. Any other questions?
On the last line that you wrote, shouldn't there be an m in the denominator?
Of course, yes. Yes, there is an m here. So what is going on today? Shame on me, right? Okay. All right. So, okay. Any other questions? All right. So let's see where we are. As I said, we are going to a little bit focus on this underdamped systems and study this in more details. There are a few things that we want to learn here, okay, which I call them observations. These are the important observations. The observation number one is, which I already actually discussed, that if damping is equal to 0, you do get this form for the equation of the response, which is for the undamped system. So this was, in other words, this formulation is a general form, and a special case would be this. If we have the initial conditions, okay, and we substitute for these values, being u at time equal to 0 and u dot equal to 0 would be the velocity at time equal to 0, u of t, okay, we saw that we derived that equation, and this is another form of that, e to the minus zeta omega n t times 1 plus omega n t plus u dot naught t e to the minus zeta omega nt, okay? So the third important point that we want to discuss is that what is this damping ratio? How do we find that experimentally? As I said, this is a characteristic of the system. So let's look at that. You're going to be doing in the lab, and you will be plotting the vibratory motion of an underdamped system. You will see that it's going to look something like this, okay? Maybe, like this, which, as we said, this is that exponential decaying envelope. So let's look at this response, which is the time response of the system. What I will do, I'm going to look at, choose two peaks, consecutive peaks in this motion. Maybe this one and this one, or this one and this one. In other words, basically two peaks, which obviously are one period apart, okay? So if this peak is occurring at some time Tn and Tn plus 1, Tn plus 1 is Tn plus 1 period. Now, let's look at the ratio of these two displacement at Tn and at Utn plus 1. So I will just write an expression in terms of that ratio of these two. But you know, you remember U is in general form is like this, right? Minus zeta omega nt times sine of omega dt plus theta. So what is un? Is the maximum value of this function, right? That is when sine is 1. So un would be what? Would be just simply e to the minus zeta omega n times t n plus 1. And un would be e to the zeta n t at n. So that would be the ratio of these two, those two peak values, okay? Now, if I substitute that in here, what do I get? I get this ratio is zeta omega n, okay, times Tn plus Td, and this is E minus zeta omega n times Tn. So you can see that easily, right? This is e to the minus zeta omega n Tn times e to the minus zeta omega n Td divided by e to the minus zeta omega n Tn. So this cancels out. So this ratio then is simply e to the minus zeta omega n Td, right? But what is Td? Td is what? Is 2 pi over omega d, okay? So let me substitute that for that in here. And so let's just do that. And also we know that omega d is 1 minus zeta squared omega n, okay? So I will just substitute that in here. So I get e to the minus zeta times omega n, which from here, omega n is what? Is omega d over this radical, right? So I substitute for that in here. So omega d divided by 1 minus zeta squared times td, which is 2 pi over omega d. This and this cancel out. So I get delta is e to the minus zeta times 2 pi over 1 minus zeta squared. Look at this relationship. Experimentally, when you're plotting this curve, let's say you can look at the oscilloscope and you plot this, right? You can measure this. You consider two successive peaks, divide those. That's what this is. Left-hand side is this exponential function is in terms of zeta. So from that, you can find zeta. However, to make our life easier, instead of writing this relationship like this is what I will do. I will take logarithm of both sides. So in other words, let's introduce this quantity being the natural log of delta. So delta, which is going to be the natural log of this, which becomes what? Becomes minus 2 pi zeta over 1 minus square, okay? Or now, if you look closely, when we say underdamped systems, as I said before, damping ratio in mechanical or structural system is a very small value, maybe 10, 12, even, I don't know, at most, I don't know, 15%. Or it's like 0.15, right? Or 0.2. So the square of that is very, very small compared with 1. So you can approximate this, say this is almost equal to 1. So the absolute value of this becomes just simply 2 pi zeta. Okay? This is a relationship from which now you can easily find the damping ratio or measure the damping ratio of the system, because the left-hand side is a logarithm of that value that you can measure, right? And the right-hand side, 2 pi zeta. So zeta is basically logarithm of delta over 2 pi. This is a very simple and easy way to measure the damping ratio in a system. You see that logarithm was involved, and we were dealing with an exponentially decaying or decreasing function. So this approach is called logarithmic decrement. And this is one way of evaluating the damping ratio, which is one of the dynamic characteristics of the system for a given system, okay? And of course, from the time response. We'll see later on that there are other ways, in fact, easier ways and more accurate ways to find the damping ratio of a system when we discuss frequency response function. So any questions?
Yeah,
So
could you
far?
explain how you crossed out square root of 1 minus zeta squared?
I said that, if this is 1 minus zeta squared, right? If zeta
Could
is,
you lower the page, please?
yeah, oh, sorry. Zeta is usually a very small number. Let's say is, say, 10%. So it would be what, 0.1, right? Even if it is 10%. In a structural system, it's even less than that. So it's 0.1. So you have 0.1 to the square root, so it's 0.01. So 1 minus 0.01 is almost 1, right? I'm 0.01. So in other words, compared with 1, this is nothing, is almost 0. So I can assume that 1 minus zeta squared is just 1. Okay? Does that answer your question?
Yeah.
Okay. All right. So with that said, let's see where we are and where we are going. Okay? So as I said, mechanical vibrations is the study of systems when they're freely vibrating or they're vibrating due to the action of a force. And in each case, we have the system can be either undamped, now that we have the damping ratio, we use this notation, or damped, undamped or damped. Okay? So if you now look at this category, we have completely studied these two cases. Okay? So now we are going to get into a topic which is actually really the heart of mechanical vibrations. And that's forced vibration. So forced vibration. Okay? Besides the fact that, of course, we are going to look at this in both cases of undamped and damped, let's see where we are. From free vibration, we learned how you identify and evaluate these two important dynamic characteristics. So now let's see what are we going to do with forced vibration. I'm sure you're going to ask, that what is it? I mean, what do you mean by forced vibration? What is the forcing function, which is a time-dependent force that you're talking about? So in that regard, forced vibration can be further categorized. We are going to look at a few cases of forcing functions. The most common one is harmonic excitation, when the forcing function is of a harmonic nature. We also look at the behavior of the system under a repetitive load, which is not harmonic, but it is periodic. Then we also look at a general forcing function, but not too general, because you may also have forces that cannot be deterministically, in fact, identified. So the fourth category would be when you have random loads, but that random load gets us to a completely separate class of vibratory system, which we call them random vibrations. And that's a course or actually a topic in itself. So these are the three types of forcing functions we're going to pay attention to.
Professor,
Yes.
what is the word after general?
Oh, general forcing function. I'm sorry about that. I wrote it too quick. General forcing function. Like, for instance, impact loading or blast loading or step loading. There are a variety of practical loadings that they're neither harmonic nor periodic and very important in vibratory analysis of systems. We'll discuss those, okay? But these are the three categories we're going to look at. And obviously, we're going to start with harmonic forcing functions, okay? So the first case we are going to study is what? We said that forced vibration, okay, in general, again, is classified into two categories, undamped and damped. So we will start with this case, and we will look at the response of the system, okay, first. So we have an undamped system under the action of a harmonic load, and we call that harmonic excitation of mechanical systems. In other words, you have a simple system like this under the action of a time-dependent load, okay, where this f of t is a sinusoidal function or cosine function, okay? So in other words, this is the forcing function that you have, something like this, okay? Where, of course, this is the period of that forcing function. So what happens? Well, let's derive the equation of motion, right? How do you do that? We have this forcing function, we have the inertial force, the lumbar force, and then we have the force of the spring. And if you just use this free body diagram, you see that the equation of motion is derived to be of this simple form. Okay? So this is a differential equation that you have seen before. You remember? Even if you don't remember, that's okay. This differential equation has a solution that consists of two parts, homogeneous part and the particular solution. What was the homogeneous part? You set the right-hand side equal to 0, you find this, which is what we have done, right? Free vibration. Then you consider the right-hand side and then perform the solution. Whatever you find, add it to this, okay? In vibration, we use a different terminology for these two. The homogeneous part, we call this transient response, and the particular part, we call that the steady state, okay, or stationary response, okay? How do you solve this problem? I don't know if you remember or not, but which is okay if you don't remember. This is what we did. We have already seen how you do the homogeneous part, right? So for the particular solution, you make an assumption that the solution is sinusoidal. In other words, it's a function that its amplitude is unknown, its frequency is the same. So you substitute that into that equation. In other words, you have u of p is a sine omega t. You need to find derivative of this, which is a omega cosine omega t. Then you find the acceleration, which is negative omega squared sine omega t, and you substitute those into this equation, okay? In other words, you substitute those values here, acceleration and this. If you do those substitution, you see that what you end up with would be something like this, minus omega squared m plus k sine omega t is equal to f naught sine omega t. So what we are trying to do, similar to what we did for the case of undamped system, we want to find these unknown quantities, right? In this case, one, A, which is the amplitude of the steady state response. So you can see that from this relationship, you can see that this would be F0 minus omega squared m plus k, okay? So u of p is this a sine omega t, where this is a, okay? But let's pay more attention to this, okay? I'm going to write this in a nicer form, and we have a reason for that. We know omega n squared is k over m, okay? So if I write this like this, as a, which would be f0 over, I would factor out m here. I end up with negative omega squared plus k over m, okay? But what is k over m? Is 1 over omega n squared. So a then becomes f naught divided by m times omega n squared, okay, minus omega squared, okay?
Wait.
I'm sorry, this is
Professor?
k over m is omega n
Oh.
squared, right, yeah, okay? So what I will do now, I will multiply this by 1 over k numerator and the denominator. What do you end up here? You end up with m over k. M over k is 1 over omega n squared. So this simplifies to this form, f0 over k divided by 1 over omega n squared times omega n squared minus omega squared. If you further simplify this, A would be F0 over K of 1 minus omega squared over omega n squared. This ratio, that is the ratio of omega over omega n, we call that frequency ratio. That is the ratio of the forcing frequency over the natural frequency, and we show that with R. So this equation is further simplified in this form. Okay? So this is the amplitude of the vibratory motion due to a sinusoidal function. I'm going to stop here, but we will discuss this much further next time. But what I want you to think about it is this. I'm going to discuss it next time, of course, right? If you have, let's say, a system subjected to a constant load of magnitude F naught, and this has a stiffness, it's a beam, so it would be 3I over L cubed, but I don't care about that, just the stiffness. So how much is this beam going to displace? Delta. What is delta? Static displacement. Just say spring, right? So that would be F0 over K, right? Now, if instead of F naught, which is its constant force, I have F naught sine omega t. In other words, instead of this forcing function, I have a forcing function whose magnitude is the same value, but is sinusoidal. Due to the repetitive or harmonic nature of that force, what happens? Displacement now becomes what? That delta times 1 over minus r squared, right? I'm going to stop here, but I just tell you that what happens that if you replace a constant force with a force that has the same magnitude but is acting harmonically, what happens? The displacement is magnified, and this is a quantity we call that a magnification factor. In other words, due to the cyclic motion, stresses are going to be magnified, displacement are going to be magnified, the strains are going to be magnified by this quantity. Okay? I'm going to stop here and we'll pick it up from here next time. Any questions?